everyone, and welcome to today's XP Solutions XP Live webinar. My name is Gavin Fields, and I am a Senior Water Resources Engineer here at XP Solutions. Today's webinar is Sewer Modelling 101. We're going to be going over the basics of sewer modelling today and address issues such as populational growth analysis, optimisation of systems, regulation, and maintenance. Today we're also fortunate to have a special guest presenter sitting with me who is Jacob Frampton from Xylem Water Solutions. Jacob is the Brisbane branch manager for Xylem Water Solutions, and he is very passionate about pump station design, pump selection and maintenance of infrastructure. Jacob will be presenting an overview of intelligent pump control systems for sewer applications. Just quickly about XP Solutions for viewers who may or may not be familiar with us. If you've been invited to this webinar or got onto it via other means, traditionally here in Australia, we're very well known for our stormwater involvement, but the W in SWIM does stand for wastewater. So our software does address wastewater, stormwater and flooding arrangements. We take great pride in our graphical user interface and the engines that lie below those, including the 1D and of course 2D engines. And the 2D engine can be applied to sanitary environments as well as stormwater. Well, let's get started. So just a quick overview of today's session. We're going to have an introduction and go through some of the core items as we described in our correspondence, talking about growth, optimisation of systems, regulations and maintenance. I'll throw it over to Jacob to get some great insights from Xylem, and at the end I'll do a quick demonstration inside our software to give people an idea of what can be done inside our modelling environment. So quickly, sewerage. Obviously sewer systems have been around for a very long time. Some of these systems have been around for in excess of 3,000 years. I'm sure many people would be familiar with Roman infrastructure. And the Romans had their influence on places like the UK early 100s BC. But in places like Greece, we have drains like these very simple drains that were designed to take sanitary overflows or system flows away from areas where people lived. The Romans with their aqueducts, they also had latrines or toilets in their defences, for a couple of reasons. And so, why did they build this infrastructure so long ago? And I'm sure the answer is typically obvious, but obviously for amenity. We all like to keep our effluent away from ourselves, and inadvertently they actually picked up on public health, because we know that if we can keep our effluent and waste products, we can ensure that the community is better positioned from a public health perspective. So engineers, though, in more modern times, we progressed through from the pre-BCs. Over the last few hundred years, engineers and designers have been coming up with clever and sometimes novel concepts to address sanitary systems. And in the mid-1800s, that was really advanced with the introduction of pumping systems. Pumps have really changed the dynamics of sewer networks, such that we don't have to rely on very, very flat graded systems or open systems that the more longer term or historical infrastructure had to deal with. And getting closer to our current day, from the 50s and through to the 70s, systems like the SWIM environment. So again, companies like ourselves here at XP Solutions with XP SWIM or EPA SWIM relied on the SWIM 1 engine, which was developed again in the early 70s, to help us better understand, plan, design and conceptualise both local and broad-scale network issues for a sewer environment. And core items here at the bottom are just a couple of quick pictures talking about dry weather systems and diversion structures that when we have combined sewer and stormwater infrastructure, we can take those low flows and divert those to a treatment plant, or under wet weather conditions, allow the bulk of the volume to discharge to the outlet. And by all means, like in Scotland, they're very keen to minimise blockages of their infrastructure, and hopefully everyone will find that generally amusing. So how does a model predict changes to flow through a network? That's a really important part of understanding growth. As engineers in modern times, we look at development. Development is a key driver for undertaking a network assessment. And if I were developing a greenfield site, I would want to try and plan or understand the intended planning of that area. Is it residential? Is it commercial or industrial? Multi-story high-rise? I've had the pleasure of just spending some time over in China, and I've been in Beijing and Shanghai, where we have incredibly dense populations. And the land use planning has rapidly changed in those areas, and this will continue to occur in both first and third world environments. The increased density and stresses that we put on our existing infrastructure is something that engineers and organisations like Xylem will take great pleasure in trying to resolve without costing an arm and a leg. The next thing that's very important when we assess growth and understand these changes, can we prepare ourselves and plan a model that adapts and responds to those external changes? And hopefully you have access to those. Some people will consider simple spreadsheets as a useful tool to understand those changes, but when we get it to a municipal scale and understanding the performance of a treatment plant, then we need to have a better response or understanding to volumes, times at which those volumes occur, and can smarter controls be adopted in those systems. So as part of that, I want to get into a software environment to assess growth. Some very simple things we can do. We can look at how flows are derived from any given location. If I have a development area, do I have direct flows that I can measure? Do I have just simple unit flow rates, which is a very common simple tool? We go back to first year university, sewer engineer. Unit flows are very common textbooks, or the really common one, which is census-based or population-based. And we can look at what units we apply, and depending on where you sit, I've nabbed these from a imperial presentation, but obviously for the metric people of the world, flows can be defined in litres per day, litres per second if you want to go to that scale. You would then apply per population or equivalent person flow rate for that scale. Look at your catchment area. Your site was 18 hectares in area, or as the example on the screen shows, or 18 acres in fact, and you might have a certain population per area. Peaking factors then become very important if we want to assess wet weather, and I'll talk a bit more about those in a moment, but traditionally dry weather flow is a simple singular peaking factor, but some engineers will ramp up their peaking factors for wet weather flows by simply adding a multiplying factor of 5. And how right or wrong that is for your location, well, you'd need to hopefully have a good understanding of your catchment and the constraints that your infrastructure is based on. To support that information, you can then apply a temporal variation or a daily pattern or a weekly pattern. And at the end of the session, I'll drive into these particular dialog boxes, and I'll give everyone a quick view of how we can set these up. And the last thing on the left-hand side, we can use some clever smarts from a software or reporting perspective just to describe that land use on residential, commercial, industrial, or other land use types. But this is key in the development or preparation for your model to push into it. Again, just probably a similar view, but just describing that if we get to a model representation, we can nominate based on these different land use types, dry weather flows, and all of those factors. And really useful to have tabular input for these elements. Another part of growth is, again, responding to those land use changes with time. And scenario management, another key part of the civil engineer's day-to-day work. It's very typical to have 5 or 10-year horizons from a planning perspective, and then jumping out to more long-term or ultimate planning horizons. And that's typically based on your infrastructure type, material type, and how confident you are that it's been built well. I'm sure if the Greeks had thought that their drains would last 3,000 years, they might have planned it possibly a little bit differently. But regardless, some infrastructure points can last longer than others, and time will tell. Probably beyond my lifetime, how good some of the decisions we make today will pan out in 100 years. And so, other factors that affect growth over those planning horizons can relate to rainfall-dependent infiltration or inflow, and particularly when we start to think about climate change as a stormwater engineer, as my day-to-day role, those changes to climate will, in the long term, have a direct impact on the performance of our sanitary systems. Growth can also be based on those simple peaking factors I made mention of before. Let's multiply it by 5. But the issue when we have peaking factors does not necessarily help us well with understanding the volume of when the flow occurs, or particularly the time to the peak. It's almost like a stormwater person there saying time of concentration, but the time to peak on a daily basis for a sanitary system is very important. You may or may not have additional patterns of information to try and plan for certain circumstances. This is typically done in a design mode. Another final one I'll just make mention of is RTK, or measured or direct inflow information. And again, quick comment there, if you have the data. And if you were to talk to my good friend sitting next to me, he might be able to help you with that. Optimizing a system. We've gone through, we've worked out how much water or effluent we have to deal with. We then need to work out how big our infrastructure needs to be. And part of this, we need to work out how efficient mechanical components or physical components are within the network, and how does it perform not only in the short term or the initial design horizon, but how will it perform over the long term. And core parameters, of course, Q for flow, H for head, T for time, and energy at the bottom. So, of course, time and energy cost money. So variables that we can optimize inside your network can be major infrastructure elements such as your wet well design. How big does the storage need to be around your mechanical or pumped infrastructure? And then again, how efficient does the pump need to be? We'd all love pumps that are 100% efficient. I was having a bit of a joke about that with Jacob earlier, but of course we don't have frictionless systems. So friction does play a very, very important part of your rising mains, as well as the actual pump itself. So rising main design, what kind of material is your rising main going to be made out of? How resilient is it to the pumped head? Do you have cyclic issues inside that rising main? Will that rising main last or resist the number of pump cycles over a 50 or 100-year design life? Hoop stress scenarios, all of those key elements to a pipeline design should be analysed. And the most important parameter, of course, is, well, how big is the catchment? What are those characteristics we get from those growth factors we spoke about earlier? And then we get to route those, move those across the entire network. And in a municipal scale model, we get to assess pump performance from point A to point B, all the way through to the treatment plant. For wet well design, you can obviously use simple spreadsheet techniques to determine volumes with just constant inflows or unit inflows over time and determine a volume. Or you can apply more intelligent schemes to assess volume based on flow rates, depths, and scales. And there are many tools we have available inside XP Swim that can help you optimize storage for both effluent and stormwater applications. For pipes, we then need to assess your rising mains. We need to assess our gravity mains. And we can design for full flow, 50% flow for dry weather if that's a requirement from your guidelines or regulations. And in a high flow event, we may wish to obtain a freeboard, possibly below the lid of your manholes across your network, to ensure that you don't have surcharges onto your open environments or your overland flow paths or natural creeks and rivers. Another very important part too is cover, and the design of any simple sewage infrastructure set does also relate to stormwater, and that is clashes. Other elements that we need to ensure that we don't clash with sewer design are things like telecommunications infrastructure, basic stormwater, water supply, and at times, sewerage is usually the one that dictates most of those other characteristics, simply so that we can address the localized grade requirements of your network. And documents that I'll talk about towards the end in regulations and guidelines certainly have very clear requirements when it comes to minimum grades and also maximum grades at times if you're in steep country. So regulation. Regulation is very important. It drives us. We have these guidelines. We have statutory, local statutory or national guidelines, both here in Australia, in New Zealand, Malaysia, Singapore. All of these countries all have guidelines that direct engineers and designers to understand where and the extent of overflows and at what conditions contribute to those overflows. And then understanding how the collection system supports treatment plant permitting. So one of the issues there when we talk about treatment plant permitting is understanding the volumes of discharge into your river systems or ocean outfalls, understanding the nutrient requirements. The Australian guidelines, the ANZAC guidelines, talk very clearly about how much nitrogen and phosphorus are able to be discharged from a treatment plant into different types of environments. Obviously, a river system is usually more sensitive to those pollutants than an ocean outfall. And so when we get through this process, assess these local regulations, determine some of the elements that affect our design and the size of our treatment plants if you're a municipality, assess capacity, determine when capacity is reached, and then predict or plan for plant upgrades, the creation of new infrastructure, which is obviously very costly, and costly is exactly it. The summation of all of these elements typically translate directly into dollars. The advantage of modelling systems is that it's possible at times to understand through routing analysis how any individual network may perform. If you have dense areas with multiple treatment systems, it could be possible that if catchment B in this particular example is exceeding its capacity, maybe we could divert somewhere in the network and push over into catchment A to better equalise and offset a future upgrade of key infrastructure, and then at a later date cancel that connection and undertake our major infrastructure upgrade, but possibly 10 or 20 years down the track rather than up front or as part of a major development. And of course, the quality impacts, of course, do directly affect those permitting or those regulatory requirements for discharge. Here in Australia, there are some core guidelines that hopefully everyone is aware of, but one point I'll just make note of in having a chat with a few engineers over the last short period, some people weren't aware there was actually an update to the Gravity Sewerage Code of Australia, which is WSAO2, mid last year. So if you're involved in this environment, please get your hands on that updated code. The previous version of that document, if I recall correctly, was in 2004, if I recall correctly. So it's been a bit of a wait between updates. And the other really important code that's going to be indirectly discussed with by Jacob is the Sewage Pumping Station Code of Australia, which also gets into rising main design and other bits and pieces. So two really important documents. And for those of you who are from international areas, and we have some people listening in today from as far abroad as Uzbekistan in our registration, so it's great to see people from across the globe listening into today's session live, and I'm sure many people will watch this afterwards. But you can refer to these documents. They are very, very useful and may supplement your local guidelines if you are abroad of Australia. This is my last session, just talks about maintenance and what impacts does this have on your network. And of Core issues, particularly with older infrastructure, is the impact of grade. Grade is the sewer designer's nightmare. If we don't have grade, we can end up with negative slopes or depressions in your infrastructure that can result in siltation. If you have poor connections or joints, you can have intrusion, and intrusion can be in the form of simply sediment or soil, but it could also be root intrusion. So that image at the bottom there shows a very, very blocked pipe system, and quite an issue having that kind of blockage for both a sanitary system or a stormwater system, and can be quite costly to remove or repair. And whilst there are many companies who certainly have the tools to get rid of that kind of an obstruction, it is not cheap. And simply clearing it out on day one will likely mean that it will simply come back, unfortunately, very rapidly. Trees are lovely at growing their roots quickly. Other aspects that poor grade or poor design affected by odour, and odour can result in corrosion with accumulation of H2S or hydrogen sulfide. And if we have hydrogen sulfide in our systems and poor ventilation, properties who live near the ventilation points can actually be subject to toxic implications. So very, very important that we understand hydrogen sulfide. And so that last point, it's at times possibly operational changes, and this is something that Jacob will definitely talk about. Operational changes can improve the performance of these systems and therefore reduce maintenance. So if we have ventilation like we have in that image on the bottom right-hand side, I certainly wouldn't want to have concentrations greater than about 10 micrograms per, I hope I get my units right here, but per effective litre of air. Otherwise, we could get to a point where hydrogen sulfide, which is a gas that smells like rotten eggs, it gets to a point where our noses switch off. Our olfactory systems are simply immune to hydrogen sulfide, and when we get to that point, unfortunately, it's lethal. So be very careful if you're inspecting these systems, opening lids. Make sure you vent them before you crack open a pump station and inspect these systems. We wouldn't want you to fall in and be very, very careful with hydrogen sulfide. But of course, hydrogen sulfide, when it's subject to exposed to water, can actually convert to sulfuric acid, which becomes H2SO4. And that's the process by which usually the side crowns of pipes corrode and the crown of the pipe falls in on itself. And again, we have a major maintenance issue. So right now, I'll kind of leave my component there, but I'm going to throw it over to Jacob. And Jacob is going to run through some very interesting infrastructure options from Xylem.
All right, thanks for that, Gavin. It's quite impressive, that blocked pipe before. I don't think any pump will actually be able to make it through that that blockage. So thank you for your time today. I'll start off by just a little quick overview of who Xylem are. Xylem, we're a global company. We pride ourselves on innovative technology into the market. We operate in 4 different markets. So the municipal market is probably our predominant market and what I'll be talking today about. We do mining as well, so dewatering pumps and mining. The industrial sector as well, so booster pumps and pressure pumps in buildings, and also aftermarket. So we have workshops globally, so we can actually service and back up our products. So some of the products that you might know Xylem from is flight submersible pumps and mixers. So that's today. Again, we're going to focus on flight products, and they're predominantly in the municipal market and also in the mining market. And Goulburn pumps, so diesel pumps, and they're self-priming pumps. So in dewatering applications, we use a lot of Goulburn pumps. Wedeco is another popular brand of ours, and that involves UV disinfection and ozone disinfection as well. And like I said, Luara, booster pumps, which is in the industrial market, and Sanitaire, which is aeration as well. Going on from what Gavin was talking about, and also XP Swims, I'd say XP Swims probably looks at more of a holistic approach to the network. One thing that Xylem did just recently was went to the market and just found what the key drivers were for the municipals. And what they came back with was pump station optimization. So when Xylem talks about pump station optimization, we talk about two different functions. The energy efficiency of the pump station and also the reduced maintenance. So these two factors are actually cost saving for the end user. With our R&D department, we actually came up with the Experior package. So I'll just move on to now a little section here. What the Experior package is, and what I'm really doing is localizing the energy savings down to the actual pump station. So from the inlet to the outlet of the actual pump station I'm talking about here. And the Flight Experior package involves three different parts. So we look at the hydraulics of the actual wet well, the intelligence of the pump station, so the monitoring and control, and the motors. So today, I won't go into the motors too much, but we do have IE3 motors, which are high efficient motors, and typically we get about 3% energy savings on the motors. The exciting part of what Experior is the actual intelligence and the hydraulics of the pump station. So what I'll start off with is the actual Smart Run. So the Smart Run component of Experior is typically a PLC controller coupled with a VSD drive. So one of the main functions of Smart Run is it actually finds the most efficient place to operate your pump station. So typically on day one when you install the product, it will operate at 50 hertz. It will actually take an energy reading and a volume pumped reading per cycle run, and it will actually slow down and operate the pump until it finds the most efficient area where that pump will operate. Now, we've had pump stations out there where we've had, up to about 25% energy savings on just this energy function alone. The other positive function of this is as time changes and your pipes build up and the actual system changes, the Smart Run will actually adapt to that and start operating the pump in the more efficient area. That's one function. That's the energy saving part of the Experior package. What we've also got is the pipe cleaning function. So when you start slowing down your pump station and operating at lower hertz, you actually change the velocity in the pipe work. So the problem with that is you might get sedimentation build up in your pipeline. So what the Smart Run does is once a day, it actually ramps the pump up to 50 hertz, 100% speed, and flushes out all that line. So over time, you don't have any blockages or any roots growing in your system. Another good function that we have is the pump cleaning technology. So the Smart Run actually does, it detects if there's a pump blockage, and what it will do, it will actually put the pump into a reverse polarity and reverse the pump and try and unblock that pump. Now it will go through 8 cycles, until it unblocks. Now after that, it will send out an alarm. Another function of the Experior package, of the Smart Run, is the sump cleaning. Now to reduce blockages and reduce the maintenance call outs, it's important to have a clean wet well. Now, what the sump cleaning does is it once a day will actually bring that water level right down to snore. So that water level, any solids or any grease buildup in the wet well will actually be sucked up into the pump and moved on and won't accumulate in the wet well. On top of that, we've also got the normal high inflow function. So once we get to a certain level and one pump at say 35 hertz can't handle the inflow, it will actually detect that and bring in the second pump. That's the Smart Run section of the Experior package. So like I said, out of that we get probably about 25% energy savings, but on top of that too we have reduced callouts. And if you take into account 3 men, 1 truck on site, going out to a call out, it becomes quite expensive. You've got a trouble pump station, you could be talking thousands of dollars over the year. So moving on to the hydraulic side. So what we've done at Flight is we've realised that we're using the Smart Run, we're using VSD, essentially we're slowing the pumps down. What we need to do is actually find we've changed our impeller design. So with the end impeller, we're getting around 80 to 70% total efficiency, which is very good for a sewerage pump. I think typically you'd probably be looking around 65% efficiency on most other impeller types. But we've gone away from that old design of actually creating a throughlet to allow solids pass, because it's very rare that you actually get a golf ball size solid coming through a pump. What we look at is actually ragging, because ragging is probably the predominant problem in sewerage. And as you can see there's a rag coming up through the inlet, and what we've done is we've got a groove in the wear plate of the pump, and what that groove does is it feeds that rag through the volute. Now, to actually help with that, with the passing of rags as well, we've got the adaptive impeller. So as you can see here, rags coming through the volute and into the impeller, gets passed through. If we come across a rag which can't get through that relief groove, what the impeller will actually do is jump up. So the next rag should be the bigger rag. It'll hit the eye of the impeller. It will cause pressure on the impeller, and the impeller will push up, creating enough room to actually pass through that rag. This technology, we've been very successful with it. A lot of problem pump stations that we've had in the past, we've adapted this technology into it, and it's been very successful. So in total, that completes the Experior package. We have done trials where we've been very successful, where we've got 57% energy savings out of some problem pump stations, but saying that, that's probably our best case scenario. Typically too, the Flight Experior package is not a one solution fits all pump stations. As with all VSD technology, we're looking at system curves with a low static head and high friction loss. So we're talking long pipe runs. That's where typically in networks you can actually save a lot of money by slowing those pumps down. The whole idea with the Experior package is to actually reduce your pump station maintenance and to save costs to the end user. So some of those points that we're looking at there is the pump cleaning. The pump cleaning function will actually clean the pumps and reduce your maintenance costs in the long term. Some cleaning as well. So what we're trying to do there with the Experior package is actually clean the wet well and reduce any of those solid build-ups in the wet well, the greases, the fats, the rags, which will eventually go into the pump and cause the pump to block, and reduce those call-outs as well. And also the energy saving side of the smart run as well. So on the bottom there too, I've got a case example. So this is a trial that we did with Unity Water here in Queensland. It was on a pump station up at Bly where we did have 50% energy savings. So if you are interested in Experior and would like to get more information on it, please go to YouTube, have a look at there, or failing that, Xylem.com is a good reference as well. So I will now pass back to Gavin. Thank you.
Back to me. I'm sort of pushing along. I want to try and wrap this up, but I just want to do a quick demonstration inside our software. And so I have a pre-built model that I have here, and for everyone, for existing clients, if you're interested, this particular model is actually supplied and available on our website. So if you've never attacked sewer design, this is certainly a model that you could have a quick look at up front, and it's in our samples folder as a sewer model. And for people who don't have our software, you can by all means contact us and you could obtain an evaluation license to the software. And I'll provide more details of that at the end. But this particular model is a relatively simple file. I'm just going to have a quick look and go through just one simple node in this relatively simple network. And if I double click into this node in our hydraulic mode, which is where we're generally interested in characteristics from a sewer network, with the exception of water quality or treatment plant design, and they occur in our sanitary mode. But information we need to supply the model include invert elevations of our manholes, ground levels, the top of our manholes, and then time series inflows is where most sanitary engineers end up. And we have this dry weather flow function. This particular option is specific to XP Swim users. If you have an XP Storm license, this is one of the very few options inside our hydraulic mode that is unfortunately unavailable. So if you are a Storm user, we would need to look at potentially upgrading to our Swim package or adding our dry weather option to your license. But under this particular file, we can nominate as many or as few dry weather flow patterns or arrangements as we wish. I'm just going to go to my default dry weather flow for this example, but we could set up residential, commercial, industrial, high-rise, parks, etc., as many as you'd like. And if I edit this particular dialog box, the information that I have available to me here talks about how the flows occur. And if you recall, these were in my slides earlier in the presentation. In this particular instance, I have a census-based model with a flow rate at, say, 125. This one says gallons per day, but if we were in metric, I might ramp that up in Queensland to, say, 225 litres per day per person. So we've said we've got an area of 1.1 hectares or acres, depending on where you sit in the world, and a nominated density at the number of people per unit area. And I can then click into the dry weather pattern. And again, we can have as many patterns as we wish. I just have a simple pattern in this example. If I edit this particular dialog box, we've gone many dialogues deep here, so it probably seems cumbersome, but once this is done once, this can apply to your entire network, and that's where our advantage is. You only have to do these components once. And we can nominate daily multipliers if we have a weekly variation based on observation in your catchment, or they could be static. You could simply set those multipliers to be 1, and then we can nominate the diurnal pattern, and that diurnal pattern will typically have peaks, obviously for the morning inflows from residential areas and also the evening peaks as well. Once we have that pattern defined and our areas nominated, we can select that one, which is this component here, hit OK, and accept that. Downstream, we can then describe what kind of infrastructure we have, and we can have circular drainage. At times, if you have a high-level overflow, we can look at what we refer to in XP as dual drainage, which means that the network could overflow to either an overland flow path or a road system at worst case. And hopefully your networks don't do that too often, but possibly only during a wet weather event or an extreme event. Nothing worse than having effluent in private property. And unfortunately, I did grow up in an area where not far from where I was particularly low, prone to high rainfall, and effluent would at times come into people's properties, into their bathtubs and the low points in their residences. So usually a big source of complaints, and an area that local municipality had to spend a lot of money to address, and in places that problem still progresses some 30 odd years later. So hopefully your infrastructure doesn't surcharge in that way. But once we've allocated our inflows across our network, we can solve our model, nominate how long we would want to run our assessment, and if I were to go through to our outfall, if I review my results, I've already I thought I'd pre-run this model, but I've moved it. That wasn't clever of me. Here we go. This is the kind of information that we can obtain from our model. So this is showing flow information on a daily basis, showing those diurnal variations, and also showing that Monday and Tuesday are peak days, whereas the weekends may have less inflow. Other parameters we can look for, which are very important for a sewage system, are velocities. And obviously these high velocities tell me that it's definitely near the outfall, but could also mean that the infrastructure is either at capacity or undersized. We've got relatively high velocities, getting up to 4.7. So that's definitely on the high side of things. But we can also assess upstream and downstream levels on that particular piece of infrastructure, and that's where we can assess the head losses or friction losses that the infrastructure is pushing back, and that could push back into a wet well. Just quickly to show a wet well, if I were to go into this particular node in the middle of this network, a wet well can be sized in our storage button inside our software, and under the storage dialog, typically people will nominate a constant area for a pump wet well, and that might be in the order of 10 square meters for approximately a 3-meter diameter manhole, or a 2.5 meter diameter manhole. And we can look at optimizing that if we're not sure if we need more volume, and we can optimize that volume based on either the size of a downstream pipe and a maximum depth that we wish to achieve inside this manhole, considering the inflows. And that's the key. So we get to understand the inflows, look at the downstream relationship, and if we need to, make this storage device bigger. Another one that I'm also a big fan of is not just changing the size of the pipes, but actually resizing the basin and the pipe. So the pipe could get bigger, or better yet, actually get smaller. We go for a larger diameter pipe, and we let the software try and pull it down. And that's the best way to get these storage systems to work. You want the largest possible relief with the smallest possible storage. And so this is a very useful arrangement, and we can nominate this depth, maximum depth here, to correlate to a freeboard at that particular location in the network. So these options are very, very simple to apply to our software. We can nominate levels at 250, which is about where this model sits. If we allowed the software to run with that optimization, it would actually run through a number of calculations. Probably the highest number I've forced this particular model to run through is probably about 75 iterations to come up with viable storages and relationships. From that wet well, the other aspect that we would possibly look at is the pumps that Jacob was making mention of before. And so if I were to bring in a pump, they go on what we refer to as a multi-link in our software, and I can relocate this network line to the other side of what I'll refer to as a pump. And in our pump, I can nominate up to 7 different pumps on this single link as a flow regime. If I click into here, I can get in contact with Jacob at Xylem and obtain core information from him about the pump type, speed factors, and other details. And an example of that information that Jacob can provide is here in this spreadsheet. This is something that Jacob did directly provide to me to prepare for this session. And we can look at the flow in litres per second versus head. And we can simply copy and paste this information into our software and create our curves. And I'll add that pump and edit it. And there we have. I could simply copy that information. I probably do want this in metric, so I'm just going to divide this by 1,000. Copy that down. Copy this information into the software. And there's my performance rating curve that can be applied to this particular scenario. It's very, very simple to apply pumps into the software, and we can nominate either by dynamic heads, static heads, well volumes, or depths in the node to control the pump. We can also have real-time control functions which can factor into your telemetry schemes. Another very exciting part of the work that SmartRun can hook into is those real-time control from pump A to pump B, again through to your treatment station. Anyway, that's basically the end of my brief demonstration that I wanted to do today. Hopefully everyone can see how relatively simple it is to certainly add data into the model. Either manually, we can import information from your GIS networks if you're building a model from electronic data up front. And this is obviously as easy for an assessment of municipal infrastructure as it is for design. So again, thank you for joining today's session. I'll really welcome any questions or comments likewise from Jacob, and and otherwise get in contact with us through the XP website and also the Xylem website, which is again, Jacob.
That's www.xylem.com.
Lovely. And thanks again, everyone. Look forward to hearing from you all soon.